Yeah. So probably by now some of you have seen me around the hallway track and in the other rooms. I'm Josh. I work at Altinity. I actually have. Look, that's me. That's what I look like. Yeah, I'm an open source advocate at Altinity. I bleed open source. Everything that we do at Altinity is fully open source. You can pay us to help you with it, but you don't have to. You can run it anywhere you want. And mostly for the lawyers, I'm going to say ClickHouse a bunch, so I have to specify. We are not affiliated with ClickHouse Incorporated. They're the maintainers of the project. We are but humble open source contributors. So, here's my hot take for today. Especially for this conference, I think this is relevant, right? Kubernetes is the Linux of the cloud. So I think a few years ago, if you asked me, for most use cases, like, hey Josh, should I use Kubernetes? And I would say probably not unless you're having these specific high availability, scalability challenges, right? These things that Kubernetes solves really, really well because it was sort of purpose-built to solve those problems. But my understanding of this is sort of evolving along with the ecosystem, and I think now the convenience of using Kubernetes kind of outweighs the convenience of having to recreate all of those things yourself, right? We have so many tools in the Kubernetes ecosystem that are available to us as like Helm charts usually, right? And then whatever method that you want to use to get your Helm charts into your cluster. So it has sort of become the de facto standard for just how to run things in the cloud. But I think running databases on Kubernetes is still a little bit scary, right? Especially for me, like these things are ephemeral, they get moved around a lot, they get killed, right? Like it's scary. So let's demystify it a little bit, right? So here's kind of a simplified view of what some of the resources and the abstractions underneath those resources that you would get when you're running a database in Kubernetes. My goal in this talk is that you understand everything on this slide and could explain it to someone else. If you need to stop me to ask questions, please do. We have plenty of time. Okay? We're going to talk about stateful sets. Hopefully you already know what pods and containers are. We're going to talk about persistent volume claims and persistent volumes, and then we're going to kind of, towards the end, dive deep into some of the different storage mechanisms that you can back those with. Okay, so how did we used to do this, right? How did we get here? Let's just go through this briefly. 2005, this is around when I was starting to charge money for doing this stuff. For me, I was on a Mac, and so for me, my development environment was SQL Pro. Is anyone else familiar with SQL Pro? Okay, it was just a macOS MySQL implementation. It had a really nice UI. It was free. I think it's still around, but I don't use MySQL much anymore. So yeah, no idea. And then in production, right, of course we had like, either we were running bare metal, if we were that type of organization, or like there was some pet VPC, right, a Snowflake server, that we guarded very, very carefully and gave as much memory as we could afford. And that was how we made our queries faster. It worked pretty well back then, right? 2015, now we're using Docker containers in development, right? Even for databases, actually, and for me at this time, especially for databases, right? Docker was very convenient to just be like, I need a Postgres, I need a Redis, I need a whatever, and I don't care if the data gets deleted. Because I'm just using this for my development environment, I have a seed script, whatever, right? Very easy. And then for production, we go, ooh, okay, I don't want to deal with this anymore. I am just going to pay Amazon to make this easier for me and to make sure that my data never gets deleted. Managed services was great for production. 2025, I'm still doing actually pretty much the exact same workflow in development with Docker. Sometimes not actually, though, because sometimes I don't have ephemeral data sets, right? Sometimes we're now dealing with data sets that are so large that it's, especially with like machine learning models and things like that, it's very useful to have a less ephemeral development environment that's maybe running in some shared server somewhere that multiple developers can access or clone. And then in production, still probably managed services or Kubernetes. So what do we need? What do we need to run a database in Kubernetes? Well, the performance needs to be consistent, right? The database is the underpinning of our application. If it's inconsistent, then just everything is going to kind of cascade from there, and it's going to be really, really painful. So we need very consistent, low latency performance. The low latency part is especially important if we're talking about replicated databases, where they need to talk, the different replicas need to be able to talk to each other before they can respond to the application. So that's really important. We want high availability, right? If the database goes down, the application goes down. We can't write anymore. That's bad, can't happen. We need to control who has access to the database, because more and more, right, these databases are being shared not just by multiple applications, but also by multiple teams that might include data scientists who are directly querying. It might include business analysts who are using tools like Tableau to create reports, right? So we need to manage access control across all of these different usage paths. Ideally, the database should scale up and down with the usage patterns. This is a little bit challenging, right? Because usually the scaling, we want to scale compute, but that might require us to also scale storage. And we might not want to scale those things separately, but we have to. So this is still an area that's a little bit of a challenge with running databases in Kubernetes-like environments. But at Altinity, we're working on some things to make that better. And I can talk to you about that after this talk. I won't get too much into it in this talk. And then finally, right, we need persistence. We need our data to never go away. We need it to still be there when we come back later. So if a pod gets moved, if an entire cluster gets replaced, we need to make sure we still have our data. That's the most important thing, right? It's the statefulness. That's the thing that makes this different from all those other things that we're very happy to run in Kubernetes. That's what makes this scary. So let's talk about why it's scary, right? Kubernetes is unnecessarily complex. I think Kubernetes is very complex, right? My issue with this, the reason I think this is a myth, is the word unnecessarily. Kubernetes is doing for us, it's wrapping all of the things that an IT ops team used to do. All of the networking, all of the integration with the hardware, all of the resource management, all of the horizontal and vertical scaling, right? It's all wrapped up in Kubernetes. That's a lot of things for one tool to be doing. So I think it's necessarily complex, but like, as I said at the beginning, it's easier than doing all of those things without Kubernetes, and you still have to do all of those things. So maybe it is actually pretty useful for that. This was very true when Kubernetes first launched in 2014, 11 years ago. Persistent volumes were first added to Kubernetes in 2016, but they weren't really fully supported until like COVID era, right, is when we start to see persistent volumes being more fully supported and sort of stabilized. But now they're very stable. Now this is great. At Altinity, we run our whole business on Kubernetes, and we're a database company. So this clearly is no longer true. And this is the final myth that I want to debunk, which is that Kubernetes comes with expensive overhead, whether that's money or performance. This is kind of true, but my argument here would be that it's worth it, right? The convenience of using Kubernetes outweighs the cost of, right? Like a control plane on EKS is about $40 a month. That's a marginal cost if we're talking about a production use case. The performance issues are a little bit challenging, right? Like if you're trying to do high performance computing and like really get the maximum I/O out of your database at really huge scale, Kubernetes is one extra abstraction layer that you're going to have to manage. It's still possible to do all the same things. It's just going to be like one extra step and, right, like one extra thing that you have to manage. So it's a little bit challenging, but it's still doable. So, okay, raise your hand if you've like already deployed stuff to Kubernetes before. All right, great, okay. We don't have to go too deep into like pods, containers, deployment, stuff like that. Here's an example deployment for anyone who has not seen one of these before. Basically, the way that Kubernetes works, right, is it just has a database, etcd usually, but it can be others, right? And we put resources in the database using the Kubernetes API, and that tells Kubernetes what we want it to do. And then Kubernetes works with the resources that it has to make the state match the state that we requested. So how do we do this when it comes to stateful applications? We have persistent volumes, we have persistent volume claims, and then we have stateful sets, which is basically just a deployment with a persistent volume claim associated with it. It has some other nice things we'll get into briefly. So persistent volume, this is just a request for storage. Very straightforward, right? It says, I want this much space. I want it to have this access pattern. The access pattern to read, write once, read, write many. Basically, it's just like, does one pod have access to it at a time, exclusive access, or can multiple pods share access to it? And then is that access read and write, or is it read only? This is fine if you just want to manage everything yourself, right? Like you can create persistent volumes, and you can attach them to pods, and then those pods have storage. but it's all, right, like you have to do all of that linking and management, you have to do all of the creation yourself. So it's not ideal, it's a little bit brittle. And that's where we get persistent volume claims, which is kind of like a template for a persistent volume, which is, hey, like, this is what my persistent volume should look like. Usually, if you're using usually this is going to dynamically create the persistent volumes for you. There's ways you can figure out where that won't happen, but out of the box, this is going to create the persistent volumes for you anytime a pod makes a storage request matching this template, right? So this is making it a little bit easier to have consistency and reproducibility, and also to make sure that that data doesn't get deleted when it's no longer attached to anything, right? These persistent volumes can be backed by multiple different kinds of storage. The most common one, especially for, like I heard before we started, a lot of us are running this in our home lab. So in a home lab environment, you're probably going to use the local path provisioner from Rancher, which basically creates these persistent volumes just using the disk that's available to one of the nodes. It's very convenient, very easy. Wouldn't necessarily recommend this for production use cases, or I'll talk about how you need to adjust this for production use cases, right? But in a development environment, this is great. And Kubernetes will handle the node affinity for you, right? So basically, if a pod gets created attached to a persistent volume, and that persistent volume lives on a specific node's hard drive, that pod will always get scheduled to that node. And the Kubernetes API will manage that for you, so it doesn't get sent over to another node that doesn't have the data that it needs. So this is great. Makes it a lot easier to just spin up storage, request storage, and get some persistence. And then we can make it even easier, right? We can use stateful sets. So this is the concept in Kubernetes that sort of adds a PVC and a deployment. I'm sorry this is so hard to read, but the slides will be available online. Right. Let's talk about stateful sets versus deployments. So deployments are usually ephemeral, meaning that Kubernetes has no issue moving them around, redeploying them on another node if a node goes down, right? Kubernetes doesn't care where they get scheduled or if they get killed and then rebooted. They get some hashed ID that's not that human readable. You can attach persistent volumes to them, but you have to do it manually. And if you're doing something like an update operation, there's no guarantee about what order the pods are going to get updated in. It's just going to happen in whatever it happens, however it happens. Stateful sets are much more useful for applications that are used to being more persistent, like running in a VM or on bare metal. So you get a stable network identity, right? You get a stable MAC address for the virtual device. You get a human readable ID on all of the pods. It starts at 0, 1, 2, 3, right? Like nice and human readable. You get managed PVCs with the stateful set template. And if you update it or upgrade it, you get guaranteed ordering, which is very nice if you have something where like you need to make sure that the leader gets rebooted before the follower for things like graph protocols. So stateful sets are very, very useful. And if we kind of zoom out to like what the stateful set looks like once we extrapolated all of the underlying Kubernetes resources, this is kind of what we get. So a very, very simplistic database deployment might look something like this. You have your stateful set that creates, say we ask for 3 replicas, right? So we get 3 pods. Each pod has its own PVC, which creates a PV dynamically. Then we have a service. I don't need to explain services to this audience. That's how you expose things, right? And then we have config maps. That's just where our configuration gets stored and gets mounted into the pods. However, this is actually not great. This is not a great pattern for applications that are used to being clustered themselves, right? Like this is a pattern that's useful for bringing clustering to an application that doesn't have its own concept of clustering. But when the application has its own concept of clustering, we don't actually want 3 identical replicas, right? Each replica with a clustered database is storing different data necessarily. So we end up with something that looks kind of more like this. And this is how we actually do it inside our cloud. We have a stateful set for each replica shard combination, right? So you get all of these different entities multiplied by each other, right? And then you get a stateful set for each combination. And that allows you to specifically manage that replica as a stateful set, getting all the guarantees that Kubernetes gives you, right? Like if it needs to have 2 temporary replicas of itself because it's moving from one node to another, it can do that. And then it can also talk to all of the other shards and replicas the way that it's used to when it's running in VMs, talking to other unique instances, right? And then to keep all of this coordinated over there on the far side, we have Zookeeper. Now you could also, if you're running in ClickHouse, you could use ClickHouse Keeper, right? But for these clustered applications, we need something that can sort of maintain the shared picture of what the universe looks like, and that's what Zookeeper is doing. And it's going to run as its own stateful set. It's a more simple stateful set like the one we saw 2 slides ago, right? Because it's okay with that. This is kind of starting to look complicated again, though, right? Like I promised that I was going to make this simple, and that's not simple. So let's simplify this. We can. We've got some useful patterns in the Kubernetes ecosystem to make this a lot easier. So these are the patterns, right? I'm going to talk about operators last, but then we also have init containers and sidecar containers. So init containers, for databases, these are really useful, right? You can also use these in your applications that talk to your databases, right? In a database pod, you're going to use your init container to run scripts that you would want to run at startup, right? Like maybe creating schema, creating users, and things like that. In your application pods, you might use an init container to check that the database is up before continuing and starting the application, right? Or maybe you want to run migrations from your application. I would definitely recommend that if it's an application that you wrote. Sometimes that's harder if you're hosting a third-party application. Run the migrations from an init container on the application side. And then sidecar containers, is everyone here familiar with the sidecar container pattern? Okay, awesome, I see lots of nodding heads. Right, so in the context of databases, these are really useful for monitoring because they have full access to the actual database container, so we can get logs and metrics out of it. They're useful for proxying and service meshes, right? Things like Istio. We can use them to pull out backups from, right, attach something to the same PVC and back it up. That's very convenient. And we can use them as an authentication gateway. Very useful. Then we talk about the operator pattern. This is really the meat of what we're doing today, right? This is how it all comes together. So operators, if I had to put it really, really simply, and this is simplifying a lot, they just translate custom resources, right? We have that etcd database with resources in it, like deployments and stateful sets and all these other Kubernetes resources that we've been talking about. And we have CRDs, custom resource definitions. So those are just schemas for custom things that we might want to create. And then the operator translates all of those things into the things that Kubernetes knows how to turn into those underlying abstractions, right? Containers and processes. So here's an example from the Cloud Native PG operator. So this is specifically for running Postgres. This is a very popular way to run Postgres in Kubernetes. And unlike all of that complication that we saw on that stateful set earlier, and then actually if we wanted replication, we needed 7 of those stateful sets, right? This is how you define a cluster in Cloud Native PG. So we've gotten it back down to very, very dead simple. Of course there are more options here, but even with like we do ClickHouse. ClickHouse is a very complicated database, but you can also get a definition that looks pretty much this simple. You say how much storage you need. If you wanted to add some extra options, like, oh, maybe we want to use separate type of storage for logs as for the data, that's probably a good idea. But yeah, you're really just creating a cluster layout, and then the operator is going to take care of the hard part for you. Right? So it's taking your desired state, and as you update this resource, the operator is going to see those change events, and it's going, oh, I need to reconcile. I need to create some new Kubernetes resources to match the new state that the human operator has requested. Operator's an overloaded word, isn't it? Okay. If we're doing this using the Altinity ClickHouse operator, shameless plug, right? We would have a ClickHouse installation, custom resource. We apply that using our preferred method for getting YAML into our cluster, and we get a working database. This gives us a lot of flexibility for how we manage those stateful sets, right? So now we can kind of scale the compute and the storage separately because the operator is handling for us the attachment of those PVCs to the stateful sets, and we say, hey, actually I need this kind of compute, the operator will keep track of it all. It will also do round robin upgrades and reboots, right? So if you change your config and the replicas need to be rebooted, the operator will make sure that you maintain high availability by rebooting them one at a time, waiting for each one to come back up with the new configuration before it moves on to the next one, right? So this is really, really convenient and gives us a lot more flexibility and a lot more peace of mind that we can kind of just ask for what we need and trust that our data won't get deleted and our database won't go down, which is, at the end of the day, the most important thing. This is a great talk from KubeCon, Salt Lake City, about how you can use Kubernetes with an operator as your DBA. This is a very nice 15-minute talk. I highly recommend watching the whole thing. I'm going to shamelessly steal one slide. Oh, sorry, if you wanted to grab the QR code. I saw a camera up, yeah. I'm going to have a list of resources at the end. This is going to be included in that. Okay, so I shamelessly stole this slide from Karen. Thank you, Karen. What does a DBA need to do? Right? Well, all of these things plus some more, but these are the main ones. Which of these can the operator, which of these can Kubernetes do for us or help with? Well, schema design, that one's really fun. I like that one. I want to keep doing it. So I'm good to keep doing that one. That's like the best part of the job, right? Availability and reliability, we already talked about, like that's what Kubernetes was purpose-built to provide, right? So yes, check on availability and reliability. Monitoring, also check, right? Like now we have all of these amazing tools available via Helm charts. It's super easy. Security, same thing, right? So we're starting to get a lot of help from Kubernetes just because we can plug into this existing ecosystem. Support and troubleshooting, hi, you can call me or come to our Slack if you need help with that. Kubernetes can't help you with that. ChatGPT can maybe help you with that, but then you can call me when that doesn't work out. Upgrades. I just mentioned, right, how the operator handles upgrades in a way that is seamless to the end user, so you don't have to think about it. Backups. The operator itself does not handle backups, at least our ClickHouse operator doesn't. We have a separate tool that does the backups. Some of the operators that I'll link to in my resources tab do have a built-in mechanism for backups. Just something to think about, right? Like you need a tool for backups that may or may not be built into the operator. It may be a separate tool. Performance tuning. Kubernetes kind of makes this easier, but also kind of makes this harder. You have a lot more flexibility, but again, you have an extra layer of abstraction between yourself and the hardware. Capacity planning Kubernetes is great for this, right? We have tools like Carpenter that are really, really good at scaling horizontally and vertically and packing workloads into nodes efficiently. So yeah, Kubernetes can help with most of these. All right, let's talk about some specific concerns when it comes to running databases in Kubernetes. Node affinity and anti-affinity. So we talked about node affinity at the beginning. We were talking about local path provisioning, right? The pod will get provisioned on it will have an affinity, right, in the Kubernetes parlance, for the node that has its storage provisioned on it. With these clustered applications, though, anti-affinity is also really important. Once you get into a production use case, you want, say I ask for 3 database replicas. I don't want all 3 of those replicas to be scheduled on the same node, even if that node has capacity, because then I don't have true high availability. If that node goes down, my database goes down, and I lose all my data. So I want to create an anti-affinity rule, which basically says do not get scheduled on a node that has another copy of yourself. Pretty straightforward. And we also want to do the same thing for Keeper, right? If we're running ClickHouse Keeper or Zookeeper in production, you want to make sure that there's anti-affinity so that you have true high availability with that service. And then, right, node affinity is useful for linking pods to specific hardware, usually is why you would use that, because you want to link it to specific hardware, storage, networking, what have you. You can also just do that if it's a specific class of hardware, you can do that just with node selectors. It's really easy. For ClickHouse in particular, we love Amazon's M7Gs. Graviton is awesome if you haven't tried it out. Exclusive scheduling. So, okay, I talked about Carpenter. I talked about packing workloads into nodes, right? When we're talking about production, and when we're talking about some of these databases, they like to be the only dog in town. right? ClickHouse especially likes to have, is like, oh, I've got all this memory. I'm going to use it all to make myself faster, which is great, unless something else needs the memory too, right? So probably you're going to want to use exclusive scheduling and set up a taint and a toleration on your databases so that each replica gets an entire node to itself. You don't need to do this with Keeper or ClickHouse, Zookeeper or ClickHouse Keeper, right? They don't need a whole node necessarily, but sometimes it can be good to do that too, just because then they're not going to ever have I/O latency from a noisy neighbor. Very important to do this for your high performance database replicas. Auto scaling. Because we have these exclusive nodes, auto scaling mostly comes down to just scaling out more copies of the same instance type, right? So we have pretty simple auto scaling rules if you look at some of the Terraform examples that are public, that are how we run our cloud. It's just a simple horizontal pod auto scaling policy. You can use more complicated ones, but you really don't need to, because we're just, you're going to probably have different node groups for your different use cases, right? Like maybe you're going to have a different type of node group for Zookeeper nodes, a different type of node group for your database nodes, and then a system node group for things like Argo CD, any of your monitoring workloads, the ClickHouse operator itself, or whatever operator you're using, right? So you probably have a couple of node groups. Okay, the storage. This is the really fun part of this talk. So, we don't just look at this. Cloud storage choices. So this is the default. If we're talking about like running on AWS, EKS, EBS, or whatever the native block storage is for your cloud, right? This is going to be the default choice for everything that I'm talking about today, and it's going to be your best first choice. It gives you relatively low latency. It's not too expensive. And it will get you will get by. It will work pretty well. And then we have shared network storage, right? Things like NFS, Ceph, Longhorn. These are awesome tools. Don't use them for clustered applications, right? Like ClickHouse is managing the replication itself. It doesn't want to be working on top of a replicated file system. Don't do that. And it's for a single node development environment, sure, okay, this is fine. Don't do this once you've got more than a single node. And then finally we have shared object storage. This is the most exciting one, right? So right now today, many databases are capable of reading directly out of shared object storage. ClickHouse can read Parquet and Iceberg files from shared object storage. S3 is going to be, on average, about 12 times cheaper than EBS, because it's 4 times cheaper and you only need one copy of the data, right? Say you're running high availability, you want 3 replicas of your data. With S3, you only need 1. So 4 times 3, right? 12x cheaper. That's awesome. And it's also infinitely scalable. And it's also one place that we can put everything. And then all of those different use cases that we were talking about at the beginning can read from it. So this is really, really exciting, but it's not quite natively integrated yet, where it's like opaque to the end user how the storage is working. That's something that we're working on. It's really, really exciting. If you want to hear more about it, ask me. And then if we're really talking about like we need this database to be fast, then we get to get into fancy kind of esoteric storage types for the Kubernetes world. Not that fancy if we're just running bare metal, right? But we're using local path and NVMe storage in Amazon. And this is where there are some gotchas, right? Like I mentioned that there's that extra layer of abstraction. So you kind of have this like chicken and egg problem where the storage is being provisioned on the local node's NVMe, but it can't be requested until it gets scheduled, and it can't get scheduled until it gets requested. And so you have to solve that chicken and egg problem using one of, like, there's like 3 janky workarounds for it right now. Pick your poison. But it does work, you can get it working, and then you can get some really, really, really high performance. How am I doing on time? Good, okay. All right, so we're getting to the home stretch here. My slides are getting redder, right? We have a complete single tenant deployment. This is how we do things in our cloud. So we have our ClickHouse clusters. We have our Keeper clusters. We're using Helm or just plain Manifest mostly to manage that. We're using Prometheus and actually Victoria Metrics, who is a sponsor. We run them in our cloud, even though we're a competing database company. Their tool is awesome. We're using Grafana. That is also an awesome tool. And then, of course, we have our operator, right? And all of that is running on AWS EKS. We use Terraform to version that. We have an open source Terraform module that's just one single command, and you'll get basically this. That's in the resources. What else do I want to say about this? Oh, this is how we run a single tenant, right? We run one of these for each one of our customers. So we run a whole Kubernetes cluster per tenant. For us, as a database vendor, this just works out. You might want to do that. You might also want to do this for your production environment. You probably don't want to do this for your development environments. It would get cost prohibitive. So there are ways to kind of like simulate this. vCluster is one of my favorite tools that I use to like simulate this so I can have something that looks exactly like our high availability production layout, but I can run it on a single Raspberry Pi, which is pretty awesome. Yeah. Yeah. 16, get one 16 gigs if you want to run them on. But all of this will run on 16 gigs of RAM.
It took a sec for me to sink in.
Yeah.
I was like,
and that's also in the resources. I have a blog post where I do that with 3 of the 8 gig models, but yeah, you can do it with one 16 gig. Okay, and then if we talk about like where this is going, and this is kind of like where I hinted at, like we're working on this. The idea is that in the future, this might be kind of opaque to the end user, right? So we'll have a database with its local cache that's like NVMe or RAM, right? It's really nice to keep the indexes in RAM because then you know exactly which storage you need to talk to before you talk to the slower storage. So you keep your indexes in RAM, then you talk to your EBS or your NVMe storage. That's maybe where you keep things like materialized views. Who's familiar with materialized views? Oh, okay, cool. So materialized views, really cool concept from analytics databases, where basically as we're ingesting the data, we aggregate it into the dimensions that we care about, right? So that our reads are then really, really fast across the dimensions that we anticipated. So right, you're keeping your important materialized views in this hot storage, and then everything else goes off to the cheap, infinitely scalable S3. Right now we have the read path working. We just released this last month. The write path we're working on. And if you would like to contribute, I would love to hear from you if you're a C++ developer. Yeah, I would really love to hear from you. I think that the database of the future will work like this. I think that it will combine the best of all of these, right? I think it's going to have the fastest local caches in RAM. It's going to have local storage for hot data, and it's going to have shared object storage for everything else. I think DBAs are going to have to worry about this, and I think end users are going to get to just run their queries and benefit from the speed and scalability of this. Here's the resources and QR code if you'd like to grab it. Those will also be available in the description of the YouTube video. Yeah, questions?
First.
Oh.